Hi, in this video, I am discussing a question related to a capacitor in a charging circuit. The circuit diagram and the question is shown on the screen. Okay, in this circuit, a capacitor of capacitance 5 microfarad is connected to a circuit as shown in the diagram. When you switch on the circuit, but I didn't show the switches. This circuit consists of 4 different standard resistors, R1, R2, R3, R4, and 3 different cells. Okay, during the charging process, there won't be any current flow in the region between the plates inside the plates of the capacitor. There won't be any current flow because the region between the parallel plates is filled with a dielectric material that will never allow current or electrons to flow between the plates. So during the charging process, what do you mean by charging a capacitor? Means electrons will be transferred from one plate of the capacitor to the other plate through the external circuit. So what is external circuit? Means the wires connected to the terminals of the capacitor. So along on those wires, there will be current flow due to the flow of electrons from one plate to the other plate of the capacitor. During the charging process, the current flow in the external circuit, we call that wire. Those wires, those are connected to the terminals of the capacitor. We call the external circuit that forms the external circuit. During the charging process, current flow in the external circuit decreases exponentially according to, that I equal I naught e to the power minus t over RC. But we don't need any of these equations in this question. I'm just telling additional information. So the capacitor charging during the charging process, current flow in the external circuit decreases according to this equation. Means finally, when we say the capacitor is fully charged, the current flow will become almost equal to zero. Practically, it will take infinite time, but theoretically it takes infinite time. Practically, the current flow will become almost equal to zero after almost 5 RC, the time of 5 RC. So where RC is called time constant, right? So anyway, but those are not related to this question. Only thing I want to say, during the charging process, the current flow in the external circuit will become almost equal to zero. We can take it as zero at the end of the charging process. That means when the capacitor is at steady state. So when the capacitor at steady state, the current flow through the wires, those are connected to the terminals of the capacitor. There won't be any current flow. Means there won't be any current flow through this resistor at the steady state. Okay, so I need to find the energy stored in the capacitor at steady state. Means I can find the energy by using E equal half CV squared, where V is the voltage across the terminals of the capacitor. We say that is the voltage of the capacitor. So I need to find the voltage across the capacitor at steady state. There is no current flow through this resistor at the steady state. Means in this circuit, I don't need to consider this resistor. Okay, so finally, anyway, I need to find the V because C is given 5 microfarad. I need to find the V, that's the voltage across the capacitor. To find the voltage across the capacitor, I need to find the current flow through these branches and through these resistors. I need to find the current flow first. So how can I find the current flow? By using Kirchhoff's second law. I need to use Kirchhoff's second law to find the current flow through these branches and the resistors. No current flow through this resistor at steady state. Okay, if I am using Kirchhoff's second law, I will start that. I will name the junctions. I can call A, B, C. This is D. Then this is E, F, G, and this I call it as H. No current flow through this component. Okay, if I find the current flow through these resistors, then I can find the voltage across the capacitor. I'll explain how to find the voltage across the capacitor. But anyway, I need to find the current flow through the branches. Okay, I'll take the current flow through this, the current coming out of through this cell. If I take it I1, so here also I1 is flowing. Through this one, current I2 is coming out. So here I2. So at this junction, according to Kirchhoff's first law, I am taking I1 and I2 are joining together and form I1 plus I2. You can take anyway. If you want, you can take current I1 is coming here, it's splitting here. Anyway, you can take it, no problem when you are solving Kirchhoff's second law. But when you solve it, you will get the proper values for the currents you mark. Sometimes you might get a negative value for the current. If you get a negative value for the current, then you should take the direction opposite to the direction you marked on the diagram. You know that, Kirchhoff's second law. Okay, so current I1 and I2 join here. So through this also, I1 and I2 flows. I1 plus I2. So the current which comes out through the terminal of a cell should reach the other terminal. So here current I2 should reach this cell here. So here it should be I2. Right. So I1 plus I2 flows. I2 flows here means here I1. So here also I1. That I1 flows through this one to the terminal. Okay, then I can use the Kirchhoff's second law for this circuit. I'm using for the circuit F, G, C, D, E, F. F, G, C, D, E, F. I am using the Kirchhoff's second law. You know, total EMF in that closed circuit is equal to total potential across the components. Total EMF in this closed circuit, this is 2, this is coming, that EMF will be this direction, here also EMF will be this direction. So 2 plus 3 is equal to total current flow. So this in this one, I can consider the current flow. This is 3 in I1 into 3 plus here in this one, I1 plus I2 into 4 here I1 into 2. Solve it. So 5 equal 3I1, 4I1, 2I1. So 9I1 plus 4I2. Keep it as first equation. Okay, so then consider this closed circuit A, B, C, D, A. In this closed circuit, if I consider, the total EMF is 6. So 6 equal to this resistor I1 plus I2 into 4. And there is no other resistor in this closed circuit. So this I can write 4I1, 6 equal 4I1 plus 4I2, second equation. Okay, so there are two unknowns, I1 and I2. We have two equations, simultaneous equations. You can solve it by using your calculator or you can solve it manually. So I'll show how to solve it manually. So if you subtract the second equation from first equation, you will get minus 1. 5 minus 6 is minus 1 is equal to 9I1 minus 4I1, 5I1. So I1 is equal to minus negative 0.2 ampere. Okay, so what do you mean by this negative value? I took the current is flowing this way, but it says negative 0.2 means current is flowing this way. So I need to reverse the direction of I1 everywhere I marked on the diagram. I'll do that. Okay, so then we'll find the I2 by substituting this in the second equation. If I substitute this value, that will be 6 equal 4 into minus 0.2 plus 4I2. Solve it for I2, you will get 1.7 amperes. So I2 is 1.7, I1 equal minus 0.2 amperes. Okay, so I am going to mark the direction of current again on the circuit. So I am going to remove the values which I marked, the notations what I marked I1, I2, and I'm going to substitute the numerical values. So I2 is 1.7. So there's nothing wrong in the direction I put. I2 is 1.7. So I'll mark the I2 here. That is 1.7. So this is also 1.7. Okay, I showed the actual current flows on the circuit. Earlier, I marked the I1 this direction. So I know I1 is negative value. So I1 should be this direction, which is 0.2 ampere. Here I marked I1 plus I2. That's here I marked I2. So I2 is 1.7. But here I marked I1 plus I2. I1 is minus 0.2. I2 is 1.7. So there will be 1.7 minus 0.2, 1.5. So actually what is happening? 1.7 ampere is coming out of this cell. It's splitting here at junction C. It's splitting as 0.2 and 1.5. So 0.2 is flowing here. And here again at D, they rejoin. 0.2 plus 1.5, 1.7 is completing. This is the actual current flow after solving the Kirchhoff's second law. And we know there is no current flow through the 6 ohm resistor. I already explained that, because when it is fully charged, there is no current flow through the external circuit of the capacitor. Right. So I know all the actual current flows, we know that. Now I need to find the voltage across the capacitor. Okay, so the voltage across R1 will be equal to 0, because there is no current flow at steady state. Means V equal IR. If I use for R1, I is 0. So here the voltage across this one is going to be 0. I can say V1 equals 0 across this resistor. I need to find the voltage across the capacitor. That means voltage across the capacitor is the voltage across the junction E and the points H. That is the voltage across the capacitor, voltage across E and H. But H and A have the same potential, because there is no current flow through the resistor. Means voltage across this one is 0, means potential difference 0, means no potential across. There is no difference between H and A. So the voltage at H will be same as voltage at A. Same way, when you consider this wire, this has no resistance. We normally take the connecting wires have no resistance. So on this wire, there is current flow 1.7 ampere, but no resistance. Therefore, if you use V equal IR again, R equals 0 for this wire. So no voltage across A and D. That means voltage at A is same as voltage at D. The potential difference across A and D equal to 0. So the voltage across the capacitor, I can call the voltage across the capacitor VC. So VC is the voltage across the capacitor. That's equal to voltage across E and H. But H and A have the same potential, because there is no current flow. This resistance, the voltage across this is 0. So voltage across H and A is the same. Across A and D is the same. So voltage across the capacitor is same as voltage across E and D. VC stands for voltage across the capacitor. Voltage across the capacitor is equal to voltage across E and D. So I need to find the voltage across E and D. Okay, right. Now look at here. The current is flowing into the cell through the positive terminal and coming out through the negative terminal, then flowing through the 2 ohm resistor. I need to find the voltage across E and D. That is, I need to find the total voltage, which includes the EMF of the cell and the voltage across the 2 ohm. How to find that? Okay, how to find it? So there are two different things we need to consider. If the current is flowing into the positive terminal, and if there's a resistor connected in series to the cell, how to find the total voltage, we must know. Same way, if the current is coming out of the positive terminal and there is a resistor connected in series with the cell, how to find the voltage across the both together. I'll show how to find that. Imagine a circuit like something like this, where there's a resistor R. this EMF E1, and there is a cell, another cell connected, which has EMF E2. We'll consider that one. Okay, so here, if the EMF E2 is greater than E1, EMF of the cell, this one is epsilon 2 or E2 is greater than this EMF, then we know the current will flow this direction. So if I use the Kirchhoff's second law for this closed circuit, I can say E2 minus E1. So here I am considering E2 greater than E1. So if E2 greater than E1, the total EMF will be E2 minus E1 is equal to IR. So there E2 is equal to EMF 1 plus IR. Okay, so here you can see that E2 is the voltage across the terminals of this cell. I didn't show any internal resistance. So E2 is the voltage across this cell. If you connect a voltmeter here, that will read the voltage across E2. These connecting wires have no resistance, means the voltage across E2 is same as voltage across these 2 points X and Y. So voltage across X and Y is same as E2, but voltage across X and Y in terms of E1 is given by E1 plus IR. So that means here you can see the current is flowing into the positive terminal of this cell and coming out through the negative terminal. So the total voltage across the cell and the resistor here when the current goes into the positive terminal, which is E1 plus IR. Okay, this is first thing you should know that. Second thing, if the E1 is greater than E2, here I took E2 greater than E1. So the current goes into this terminal, positive terminal of E1. If E1 greater than E2, what will happen? There the current will come out of this direction. Current will flow this way. So there, if you write the Kirchhoff's second law, this is greater than this one, means you will write E1 minus E2 equal, current is flowing this way, equal IR. So there you will say E2 equal E1 minus IR. Okay, in this situation, you can see E2, the voltage across this one, okay, is equal to E1 minus IR, that is the voltage across XY. So voltage across E2 is same as voltage across XY, which is given by E1 minus IR. That means if the current comes out of positive terminal of the cell and if there's a resistor connected in series with that cell, the total voltage across the cell and the resistor is given by E1 minus IR when the current comes out of positive terminal. If the current goes into the positive terminal, earlier situation, what I already explained, there it's given by E1 plus IR. Okay, I'm going to use this one here because current is going into the positive terminal when E2 greater than E1. So here you can see current is going into the positive terminal of the 2 volt. So the voltage across E and D, compare voltage across E and D is similar to voltage across X and Y when current goes into the positive terminal of this cell. So voltage across E and D is the voltage across the capacitor, I already explained it. So voltage across E and D is given by 2 plus 0.2 into this resistance. So as I explained now, VC equal VED, that is 2 plus the current flow 0.2 into 2, so that is 2.4 volt. So energy stored in the capacitor E equal half CV squared. V means VC, I can say half C, VC squared. VC is the voltage of the capacitor. So that is going to be half 5 microfarad 10 to the power minus 6 into 2.4 squared. Solve it. You can give it in microjoule. So that will be 14.4 into 10 to the power minus 6 joules, or you can say 14.4 microjoule. That's the energy stored in the capacitor at steady state. I hope you understood this.